Yeah, so very many thanks to the organizers for inviting me. I very much enjoy being here. This is work with Andrew and Pablo. I'm currently in Singapore, but next week I will be in Delft at QTech, which is some kind of new quantum initiative which exists since the summer, and I think it's going to be very exciting.
Steph, okay. I already have a question. Are you sure it's not 15?
Yeah. No, I'm pretty sure it's 14. Yes. So I have some good news and some bad news. Should we start with the good news or the bad news?
Let's get the bad news out of the way.
Bad news? Okay. So, even though I'm obviously one of these quantum people, you can already see it here. There will be no beautiful physics pictures in my talk.
What's the bad news?
The good news is, the possibly good news, at least for some of you, is that I have tried to eliminate any and all quantum notation from this talk. And I will make an attempt to kind of, I guess, communicate maybe in a language that is more familiar to you. If I do sometimes use some wrong terminology, please bear with me. I'm trying, so slowly, like in 40 or 50, maybe. Okay, so I guess you know all about what we want to do. So we want to maximize or minimize some polynomial over some space V. So what is this V? So let me give you some examples that in particular will be interesting in this talk. So for example, V might be the hypersphere of dimension n. It could also be a complex projective space. It might also be a discrete object like the Boolean cube. But what I'm going to say is also going to apply to general Riemannian symmetric spaces and nice discrete objects. So for example, if this was like over a ternary alphabet, then you could play the same tricks. Even though we will see in the end that you need to know a few things about the space V, in particular some properties of orthogonal polynomials relevant to V, but I'll get back to this. So what is going to happen in this talk? So if you only remember one thing, then this is, you can read our paper in the nearby future. So we have some general procedure to obtain convergence bounds for semi-definite programming hierarchies. And these convergence bounds are based on so-called kernel functions. I will explain to you what that means. So for every kernel, there will be some kind of convergence guarantee. It encompasses some of the existing hierarchies. In particular, I guess, for the quantum people here, also the way of writing it on some kind of tensor products of systems, if you want. We will obtain explicit representing measures, and in particular, we will also get some improved convergence bounds for optimization over the hypersphere. So this is some example that I'm going to discuss in particular. So like I said, our results apply to all kinds of objects. However, for simplicity, for this talk, just always think about the sphere. So what I want to do is I want to optimize this polynomial in some variable x. So x is like n elements. And I want to live on the sphere. So basically I have a spherical constraint. And I want to find the maximum or minimum. So I mean, I guess you all know what polynomials look like. This is some polynomial. So kind of, how difficult is this problem? If the polynomial has degree at most 2, then this problem is actually easy. So I guess this is a problem, for example, for this polynomial on the sphere, it's easy. But for degree larger than 2, in fact, the problem is NP hard. So I guess you're familiar with these kind of results. So for this polynomial, for example, I guess this is quite simple. It's difficult. And so the question that I'm going to be concerned with is kind of, okay, so finding the exact solution is kind of difficult. So how difficult is it to approximate the max? So I'm going to list some results. These are non-exhaustive. Aram already gave you also this earlier. So if you want to know, there's actually a survey, which I guess by now is a little bit older, that discusses optimization over some objects like this, the sphere simplex, the sphere, and the cube. There's also some approximation algorithms for a very special class of polynomials, which are called focus polynomials. There's also some special cases considered in computer science. I guess Aram talked about them earlier today, which are basically sums of products of polynomials of low degree. So there's also some results by Fajbusonic, going back to earlier results for Resnick, which gave some approximation guarantees for SDP hierarchies if I'm interested in optimizing the polynomial over the sphere. So there were some earlier results by Andrew and myself that obtained using some kind of quantum-inspired techniques, very similar approximation guarantees that had previously been obtained by Fajbusonic, using, however, quite a different method. And in particular, you can understand what's going to happen in this talk as actually a much more general version of what we're doing here. You might argue that if you were to truly understand the proof here, why it actually works, then what I'm going to discuss is going to be very natural and also give something better than what we have here. Yes, so I'm also exposing you to my handwriting. Okay, so I guess you are familiar with this, but let me maybe briefly summarize. So typically when you want to optimize a polynomial over the sphere, you could also ask, let me optimize the following. So I'm optimizing over all measures, which here are called mu. So you should be thinking about this here as some kind of probability density on the sphere. So I'm calling this a probability measure because I really want to emphasize that this is normalized. So of course now we haven't really gained anything. It's just as difficult as solving our original goal. But I guess you're all familiar with this. Writing it this way now suggests a very natural way to relax the problem, giving a hierarchy of semi-definite programs that will get us closer and closer to this true optimum. So let's say that I want to optimize over measures. So here I've just written what we had before. So I want to maximize the following. So here my LM, I will call it M here, to indicate that really here I'm optimizing over a true probability measure. This true probability measure satisfies a few properties. So for example, it is normalized, meaning that I integrate the whole thing. So in this notation, meaning that I evaluate it at the constant function. So I guess from optimization, you are very familiar with this kind of way of writing this as some kind of pseudo expectation. For the quantum people here, you might think that I'm taking the trace of the density operator. So this is equal to 1. And of course, the next thing that I want is I want that these things here are positive. So the idea about forming these relaxations is to now keep one. So we're going to keep this positivity constraint. So we're going to demand that over in the constant function I evaluate to 1. But here I'm going to relax the positivity constraint and I demand that I'm only positive for when evaluated at squares of polynomials that have a certain degree, L. So of course it depends a bit what L is. So the larger and larger I make L, the kind of closer and closer I get to this positivity constraint, because if positivity is true, then this is true for all degree polynomials, arbitrarily large L. So you can think of this L here as kind of telling us which level of the hierarchy we're at. So this relaxation looks like this. Let me just write it again. So here we're maximizing or minimizing over the sphere. So I'm minimizing some polynomial such that I'm normalized and I'm positive up to level L, so to say. And if I'm on the sphere, I also want to have the constraint that, well, I am indeed located on the sphere. If we actually write down the SDP in terms of matrices, I guess this would make it more obvious to you. To me, maybe it's obvious to you from this notation already, that like this one I don't need to write down explicitly anymore. And in fact, what's going to be relevant is going to be constraints 1 and constraints. So what have we done? So note that we've relaxed the problem. Okay, so if I'm minimizing and maximizing, so note that here I've kind of enlarged the set of matrices that I'm minimizing over. Okay? So actually, this is from some earlier talk where I was actually maximizing. So I got this, the SDP solution was larger than the original one. Here, because I now changed this to your notation and I'm going to minimize. Of course, this minimization gives us a smaller value than the original problem because I allow more L's. So what I'm going to do now is I'm going to talk about what I'll call, I don't know, kernel-based rounding. Then I will talk about the approximation guarantee that will derive from this. And in the end, I will talk about how to choose the right kernel, or well, a kernel that gives us a good approximation guarantee. So let me first say a bit about what is a kernel and what properties of this kernel am I going to assume. So again, maybe for the quantum people, given that I've converted everything, you might say, how about my favorite SDP hierarchy? I want to write it down on a tensor product of spaces. So you might do this. This is a special case of what I'm going to do. But I'm not going to talk about this. So what is a kernel? So a kernel is a function from like our space V, so for example the sphere and the sphere, to the set of real numbers that can be diagonalized. So I guess we should be thinking about this in terms of matrices, in the sense that I can diagonalize it in terms of some eigenvalues, so these lambdas then, and some eigenfunctions. So you can think about these as being functions which are also normal with respect to some measure, the uniform measure on the object that we're interested in, for example, this sphere. So let me give you an example of this, a kernel function. So for example, one possible kernel, which is called the polynomial kernel, is I take the Euclidean inner product of two vectors x and y on the sphere, and I raise it to some power s. So in fact, it turns out that what Andrew and I were doing earlier, in fact, this is the kernel that we were implicitly using, but we'll be using some more general set of kernels. So let me tell you a little bit more about kernels. So I guess most of you are familiar with this, but maybe some people not so much. So just like with matrices, kernels can have degenerate eigenvalues. So this just means that like it's possible that this lambda j occurs here multiple times, same value. And if it occurs multiple times, I can kind of bunch these eigenfunctions here together into spaces, kind of depending on the same eigenvalue. So let me define Rm. So here I bunch all of these together that have eigenvalue equal to lambda n. And of course, I can just rewrite my kernel then in terms of lambda n. It's the same for all of the ones that I've bunched here, times this Rmx. So I'm calling it Rmxy because it is itself a kernel. And in fact, it has a property that is called reproducing. So what does this mean? So this kernel here is reproducing for all functions f, which I will call m, which are in the span of these functions ej here, namely such that the eigenvalue lambda j was equal to lambda n. What does this mean to be in the span? So it just means that I can write f as some combination of these functions ej. And we give this space a name. I'll get back to this later. So let me call this here hj. So this is basically the space of all these functions. What does it now mean to be reproducing? So this R is reproducing for this space of functions hj. If for any element, I have that if I take the integral so over the sphere with respect to the uniform measure of this function and this reproducing kernel, well, I get back the original function, now evaluated at the point x. So you can think that what I'm doing here is that basically this here is a kernel that is kind of, if I kind of take this integral, is constant on this particular space of functions hj. So let me say a bit more about this. Of course, you already know one particular kernel, namely the fully reproducing kernel. So fully reproducing means that this holds not just for some functions in some subspace of all possible functions, but indeed for any function that I might want to write down. Okay. So if I integrate like f with respect to the uniform measure, fully reproducing kernel R, then I always get back f x. So you know such a function, like the delta function. No, I'm not quite sure if I'm using the right notation for you, but some people like to write it like delta xy, which is the same as the fully reproducing kernel in this language. So I hope this is kind of clear. And I want to point out one thing. So I had said what are eigenvalues of a kernel just one slide ago. So if we think about what are the eigenvalues of this fully reproducing kernel, so these here are all 1. Okay? So it's completely flat. They're all 1, and this makes the kernel fully reproducible. This is something useful to keep in mind.
So you can think of the sum over Rm as the delta function.
So in this talk, I will be interested in kernels, which I will call valid kernels. So I will call a kernel valid if it has the following form. So first, it satisfies this property, namely it is in fact the square of another function, zeta, of x and y, such that this here is a polynomial in y of degree at most L. Okay, so L will be the level of our hierarchy. So this is property number one. It's now not quite clear where I want this, but I remind you. And the second one is that in fact the polynomial that I'm interested in can in fact be expressed in the following way. So I can write it as a sum over j of functions pj, such that pj is an element of this hj. So note that my kernel defines these spaces. I'm going to diagonalize it. I write down its eigenvalues. Then will be these spaces defined by these reproducing kernels rj, corresponding to the same eigenvalue. So maybe to kind of give you an example of what you should be thinking about here. So actually for the remainder of the talk, it's useful if you think about the space hj as the space of all monomials of degree j. So if you think about spherical harmonics, for example, on the sphere, think about this as being the space spanned by all spherical harmonics of degree exactly j.
Sorry, I don't understand the connection between the second condition and the definition of valid. Like, how does that have to do with kernel?
So I just want that, the thing is I could basically, this definition 2 just says that my kernel, if I diagonalize it, gives me means to write my polynomial in terms of the eigenfunctions of the kernel. This is all that condition really says.
Oh, I see. There's R from that kernel. Oh, I see. Sorry. And the dependence on zeta can be arbitrary?
So I will, later when I optimize over kernels, I'll make this more specific, but in the moment just think about this condition. Okay, so condition 2 is just to ensure that I can write the polynomial of interest in terms of functions in which the kernel is also diagonal. So I will assume some notation here. So H0 I will call the space of constant functions. And Hj will be the space that I had just defined, where these Rj's come from the kernel. So let's consider some kernel like this. And let's see what we can now actually do. So remember that we actually wanted to solve an SDP. Okay? So let me call new SDP the kind of optimum that I get when I actually go and solve this SDP. Okay? Some particular chosen. So it's not difficult to see. In fact, especially in this kind of abstract notation, that there exists some signed measure such that I can write this L in the form of a L. So I'm not sure that this is how you usually write it down, but I find it useful to think about it like this. Because so here we have something which I guess in quantum information or quantum optics one likes to call the P representation function. And in fact it turns out that one can take it to the polynomial of degree at most 2L, where L is the level that we have. So if we solve the SDP and we find some kind of L, then there's some way that we can write it like this.
So, I'm sorry, the reason this is not, if it were not signed, then this would be exact, but the problem is that it's signed.
So there's already a good point here. So if, in fact, this was like a true measure and not a signed measure, then this would always be positive and we would already be done. Because note that normalization is already satisfied. So if this was all positive, then in fact this here would be some kind of probability distribution and we would have found a solution. But sadly, so we can only know that it's normalized, but it's not necessarily positive. So the question is kind of how can we turn this I guess, signed measure into a true measure. So we want to round this. So the goal of what I'm going to discuss is to find the true probability measure, mu q, so in quantum optics this is also called the Q representation, such that an approximation, which I will call LP, where I've basically, all I've done is I have taken P and I replaced it with Q, has the property that this closely approximates LP. So I want that the difference between the actual SDP solution and the approximation that I just constructed is smaller than some epsilon, which I determine. Yes? You can stop me anytime. So how to form an approximation? So I will write it down explicitly, but you can think that it's defined actually by evaluating this at functions f. So this is what I want to define. This is what I'm doing. Okay. What I've done here is I've written Ly merely to indicate that here I'm going to integrate over y. Okay. In the SDP solution I had omitted the L because it was not so important. We had only one variable. Now let me write it on y. So L of y at this kernel here. So I write k of x to be the kernel function where I fix the x element and I vary over y. Okay, so I'm integrating over y. And what this will give me, so here I have f of x, and here I take the expectation, I write e of x if I take the expectation with respect to the uniform measure. Okay? So here is the uniform measure. And what is this 1 over lambda 0? So 1 over lambda 0, this is the first time that I guess that the eigenvalues of the kernel will kind of sneak in. So this here is the eigenvalue lambda 0 of this kernel. So this is the eigenvalue that goes with the lowest space, R0. And maybe remember that this corresponds to the space of constant functions. So there's a few things that we should check. Namely, we should check that it's normalized. Okay. So why is this thing normalized? So what I'm to check this, I'm going to plug in here the constant function. Okay. So here would be the constant function. I've omitted it now because it's just one. So what I can do now is, I guess if you think about this, I can commute these two things. So I can exchange the x and the y. Again, for the quantum people, I guess this is easy for me to see. You can exchange the order of the integral. So now we have some properties. Okay. So remember, in fact, that the lowest order eigenvalue can be obtained if I compute the following. So I'm going to integrate on the constant function, which just picks me off the lowest eigenvalue of the kernel. So this comes from the property of the kernel, which means that this here, in fact, is just lambda 0 times 1. So the lambda 0 goes away with this lambda 0. And then I use the property that my SDP solution was normalized in the sense that if I evaluate this at the constant function, I do
So the expectation, this isn't like a normalized expectation. Do you just mean like integrate over all x?
Where do I integrate over?
Or maybe I missed something.
Which do you mean? This one or this one?
No, on the next. So that, never mind, I'll ask you about it later.
So note that, like here, these, you can think about it just like with the matrix. I have assumed that the eigenfunctions are also normal. And that the lowest eigenvalue, the lowest space, like the 0, A0, is the constant function. Which means that this here really just gives me lambda 0. But I can show you later. So the second thing that we want to check is it positive? So to ensure that it's positive, let's remember some nice property that we had for a valid kernel. Namely, the valid kernel was a square of some function zeta xy, such that this here was a polynomial of degree at most L in y. Okay. So I know something about this, and I know from the SDP constraint that in fact my SDP solution, if I evaluate it at a polynomial of degree like q squared, where q is a polynomial of degree at most n, then this here is in fact positive. So this valid kernel together with this SDP constraint also guarantee me that this thing is positive. So maybe to make this more explicit, one other way to write this down is I could have written down so this measure that I'm constructing in the following way. So 1 over the lowest eigenvalue of the kernel, so this comes from this. Here I have my SDP solution. Again, I just write y to emphasize I'm integrating the y. Here I have my kernel, and here. So basically this means that my approximation is going to look like this. So remember, let's just take p and replace it with q. So we've now kind of constructed an approximation, but of course now the obvious question is, how good is this approximation? Or how can we actually hope to say anything about the goodness of this approximation? So in order to do this, I want to think about what is the relation between p and q. And I will look at this kind of from two different ways. The first one is I just want to, in fact, expand it. So again, here I'm summing over j, so you should be thinking that I'm doing a decomposition here. Again, if you think about the sphere, just think about decomposing this into monomials of certain degree. So j, again, corresponds to the space spanned by the spherical harmonics of degree j. So I'm going to do this for both p and q. And I'm going to be interested, what can I say about the relation between like this mu q at j and mu p at j? So to start with, let's again remember like from the previous slide, how was this mu q defined, okay? So I had written it in the following way, and I'm going to expand it, which makes this maybe a bit more obvious. So here I'm integrating, and what appears here is in fact my kernel function. And remember that my kernel looked like this. So here I have this Rj, that is constant on the space of functions j. And here I have these eigenvalues, lambda j. So basically all this kernel is going to do is it's going to tack on a lambda j on all the components. So what this means is that q at component j is just lambda j times this, where I have the lambda 0 here coming from.
Are you going to say what these are for the spherical harmonics?
Yes. So I'm going to, actually I will never write them out explicitly, because so far I have not told you yet what this kernel is. I'm later going to optimize over kernels, and then we will see how to find these. So one thing, however, that I want to point out here is that if you think about what is the relation between p and q, so the original SDP solution and the approximation that we're constructing, they're related, in fact, by the eigenvalues of the kernel, okay? In particular, this ratio. So you can think, in fact, if we had normalized the kernel such that lambda 0 would, in fact, be 1, if you want to think about it this way, then what this means here is that, remember that my fully reproducing kernel had eigenvalues all 1. And if I only were able to use the fully reproducing kernel, then p would actually be equal to q. I cannot quite achieve this. In fact, the reason that prevents us from achieving this is because we want to have this valid kernel. I will say more about this in a second. But you can already see here that what we want to do is we kind of want to make this here as close to 1 as we possibly can. So again, let me emphasize this, and if you look at this, it's kind of obvious that it wouldn't be great if like this ratio was actually equal to 1. So you can intuitively think that what we're going to try and do is we want that this here, so this kernel like normalized, is in fact a good approximation to the fully reproducing kernel. And instead of thinking about this relation between p and q, let me actually write it in yet another way that again emphasizes what we were really trying to do here. So remember that we're interested in the difference between my true SDP solution and this approximation that I'm constructing. So let me kind of expand this. So here what I've done is I've just kind of plugged in the definition of this approximation. And I've used the fact that this is reproducing to also write this here as an integral, but now with respect to the fully reproducing kernel. So what you can see appearing here is, in fact, that here we have the difference between the fully reproducing kernel and this guy here. So it would be really great if we could make this close to the fully reproducing kernel. But maybe we cannot. Okay, so what prevents us from this? So note that I had imposed some restrictions of this kernel because I wanted it to be valid. In particular, I wanted to be a square of this function zeta xy, where zeta xy was a polynomial in y of degree at most L. So you can think that what we're really doing here is we're trying to approximate this delta function, this fully reproducing kernel, by using ever larger kernels of ever increasing degree. If L would go to infinity, they would perfectly approximate this delta function, this fully reproducing kernel. But for any finite L, we can only try and kind of get somewhere in the vicinity.
Because polynomials of low degree cannot be too spiky, and you want it to be as spiky as possible.
So let me maybe just summarize what we do. So far I have not, as Aram has suggested, you're asking what are the eigenvalues of this kernel. I have not picked one yet. So choose a valid kernel. We're going to establish that there's this P representation. Here it's easy to see that this is so. For a hierarchy that you've already written down, not in this form, for example, for the quantum people on these kind of tensor product spaces, you would then have to first argue that there is this kind of P representation. You can define a Q representation using this kernel. So note that different kernels give, of course, different Q representations. And in the end, what we had done is we had approximate P with Q. Basically, we had just taken out P and swapped in Q. So now, what is the approximation guarantee that we'll be getting? And I want to state a too general theorem, and I will say shortly why this is in fact too general. And I want to specialize this in fact to polynomials which live in just one hj. So if k is a valid kernel, and I'm going to form this approximation as we've just discussed, then it's true for all j. Actually, it would have been less confusing if I had written for all j here. In fact, the following quantity is less than 1 minus this approximation ratio. So note that this was in fact what related P and Q. So now you're probably wondering, what is this kind of funny thing that I'm writing here? So I like to write it here to remind us also of these, I guess there's some kind of quantum thing sneaking in here, but only in terms of notation. In terms of that you can think that this here is a distance measure between L and the approximation L tilde that we just constructed. And how is this defined? Basically, we are maximizing over all polynomials of degree j, which are normalized. So they have one, the maximum of these guys. The absolute value of the maximum, the maximum of the absolute value is at most 1. And I'm looking at the difference here between the original SDP solution and this approximation. So in fact, what we can show is we can show this general statement, okay, in fact, that holds for all such P. And now you can already see why I'm saying this is too general. In fact, the construction that I'm going to do, I claim that it's good for all P of a certain degree. Not just the S, the one that we actually wanted to optimize, but in fact, my approximation will look very similar to my SDP solution for all polynomials of that degree. So you can see that we're actually overshooting our goal a little bit. We're proving something which is actually slightly too powerful for the original task that we wanted to consider. So maybe for the quantum people, this is quite analogous to kind of these quantum definite theorems, where in fact you want to do some L1 norm approximation. I would like to emphasize again, only for the quantum people, if you were to translate this to the quantum language, you would actually be proving an approximation in a norm that is even stronger than the L1 norm. So how do we do this? And this is why I want to do this calculation for some Pj. So we, yes.
Is it clear why there should be an infinity norm for that? You max over P with infinity norm less than 1?
Yes, so note that actually maybe going, if you think about actually the Definetti and the L1 norm, then what you have here in fact is the infinity norm of matrices.
Okay.
But here I'm interested in the infinity norm of functions. So this is actually also the difference between this norm and the normal L1 norm. So if you, in the quantum language, I'm sorry for everyone, so in the quantum language, like in the L1 norm, you want to maximize over all measurement operators M. Here you want to only maximize over measurement operators which are like X tensor L. And I'm interested in like that this here is bounded for all such things. But of course, this is I'm allowing kind of more things. I only want that it's normalized for on X tensor L instead of having the really largest eigenvalue less than 1.
So it's like H sep at most 1, or is it like? Okay, doesn't.
Yeah. So note that I have, like I said, I'm not sure whether this was so successful. I have tried to eliminate all these matrices. So this really is the norm of the function. So this here is the maximum of the the maximum of the absolute value of Pj. So, like no matrices or separable states or stuff like that. Okay, so how does this work? So this is the difference that we want to bound. So what I'm going to do now is I'm going to do the same calculation as before, where here I plugged in the definition, okay? And here I've just written it in terms of this reproducing kernel. So note that I can always do that because it's flat. So now how do I get from here to there? So note that this here only lives on the j's component. So here I'm summing over all j. Here I'm also summing over all j. Here I also have the eigenvalues. But because this here only lives on the j's component, I can ignore all the other ones. Okay? So because this here lives in h, I only get rj appearing here. So now I can, here's an rj, here's an rj. I can pull this here outside. And note that this here is again reproducing on this space pj, which means that I get back my SDP solution and this compiled pj. And so let's remember that in fact this here was normalized. In fact, for all of these guys, I guess I should have written here absolute value. In fact, this is less than 1. So now I have just an approximation in terms of this. In fact, I had omitted the absolute value in the previous line because this is going to be positive.
Ly corresponds to a measure? Or Ly corresponds to a measure?
So note that L is my SDP solution. Okay? It is my, I guess in your language, pseudo-expectation that I have obtained by solving the SDP. I'm just writing Y here to integrate, to specify always, because here I'm integrating twice, like I'm once integrating over X and integrating over Y, which is why I just put a Y, just remind ourselves that here I'm integrating over Y.
Like you're saying, like k of xy is a function of both x and y. So when you apply the pseudo-expectation operator, you could have applied it to either the x or the y coordinate.
That's correct.
But then I'm not sure about the last inequality because, I mean, like, the fact that that py is upper bounded by 1, it doesn't necessarily mean that the pseudo-expectation.
If you have a function that's as its maximum value is 1, does it mean that that for every pseudo expectation it is at most 1? I guess no.
I mean, only if it's a measure.
No, maybe j, maybe p is a polynomial of degree at most j, and y is a pseudo expectation of level larger than j than it is true. Right, because
I mean, if like the next cut.
Oh wait.
Yeah, I'm actually wondering whether I cut some comma here because I wanted to. Actually, I'm sure I don't have to think about it. So note that this is actually not quite the argument that I'm making, but I thought I could compress it to one slide. Okay, so once upon a time, some long time ago, we wanted to optimize some polynomial, okay? And I want to now make an assumption about this polynomial, namely that its true minimum and its true maximum are on the opposite sides of the zero. Okay? So the true minimum is less than 0, and the true maximum is greater than 0. So you might object to this, but note that I can easily transform my situation into one where this is the case. I'm just going to evaluate my polynomial at some arbitrary point x0, and instead I'm going to consider this polynomial piece bar, which in fact is my original one minus the value at this particular point. So note that this satisfies this condition, and in particular also if I take the difference between the maximum and the minimum, then in fact I get back the difference between the original one, because this here is just constant for this. So how close is the SDP solution to the true optimum? So note that because these guys are on the opposite sides, we also know that this here is less than the difference between the maximum and the minimum. So we have, by this, I guess, theorem, that the difference between the true SDP solution and the approximation that we're just constructing is less than epsilon. So epsilon here was 1 minus this eigenvalue ratio times this here. So when I stated it, I had assumed that this here is less than 1. Of course, maybe in general it's not less than 1. In this case, of course, you can transform it into this bound. And now you can apply this situation here to show that this is less than epsilon times this difference here. So in general, like if this is the true minimum, then the SDP solution will be less than that, okay, because I allow more matrices that I'm minimizing over. My approximation, which comes from a true probability measure, will be at least the minimum. Okay. So now using the difference between this guys here, and like I said, the fact that we've just constructed it, one can transform it into a statement like this, namely that the minimum is between, so the SDP solution approximates the true minimum from below and also from above by some factor epsilon times this difference factor here. And apparently this is how you guys like to write out this approximation. So like I already said before, like what we've done here is we've used the polynomial kernel. Here we kind of use general kernels, indeed. We have not yet said what these kernels actually are. So this is kind of, our original result was kind of inspired by quantum information, where we argued that we proved some kind of definite theorem. I would maybe like to emphasize for the quantum information people here that one could also kind of prove quantum definite theorems from the kernel perspective, where usually kind of you're interested in approximating by a certain class of states, for example, some coherent states, and this will in fact fix the kernel, so then we don't have any more choice. The eigenvalue, we just need to compute the eigenvalue. I would like to say that, in fact, if you don't work in this abstract setting, but you just write down some other SDP relaxations, then in fact, such a P representation always exists if there's unique mapping from polynomial to polynomial matrices. And in this case, I guess you have to find the eigenvalues of the kernel to obtain some approximation. So here I've kind of proceeded much more abstractly, and you're of course now wondering, how am I going to choose the right kernel? So remember that what we're trying to do is we're trying to kind of make the eigenvalues actually of our kernel as close to 1 as possible, because that would give us the fully reproducing kernel. But we don't have so much to play with, because our kernel is a square of something that's like at most degree L in Y. So we're now going to optimize over kernels, and I will restrict myself to kernels which are so-called zonal. So a kernel that is zonal has the following property, namely that it's invariant under the automorphism group of the object. Okay, so for the sphere, this is like the orthogonal group. So this means that if I rotate x and if I rotate y, then my kernel function is invariant. Indeed, for example, again, this polynomial kernel obviously has this property, okay, because this inner product is invariant under the orthogonal. The zonal functions can be simplified. For example, you can read all about it in Frank's survey, that one can write them out in terms of so-called Gegenbauer polynomials. So here again are the eigenvalues, but instead of writing like r's here, I'm writing something called Gegenbauer polynomial, where this t here, in fact, depends only on the inner product between x and y. So for the sphere, these are the Gegenbauer polynomials. For example, the Boolean cube, these are the Croucher polynomials. And there's all kinds of other orthogonal polynomials, Jacobi polynomials for complex projective spaces, and so on. So what does these look like? Again, just maybe for the sphere. So in the sphere, you could also write this out in terms of spherical harmonics, just to emphasize really what these RJs would actually be. But of course, I'm now just going to think about it in terms of these Gegenbauer. So of course, one could use some kind of established kernel. In fact, apparently, I learned from Parrilo there's something called the Wehner-Korovkin kernel, which in fact turns out, also to be the optimal one. But we can also find it, or optimal zonal kernel. So how do we do this? So let me consider this here. So actually, to confuse you, in my handwritten notes I called it zeta. Now I'm going to call it little k, because I wasn't quite sure how to. Okay, so this is the function I'm going to square. And so, I mean, this is just some function that I'm going to assume is invariant, okay? So I can decompose it into Gegenbauer polynomials and some coefficients, which I will call eta j. So these are not the eigenvalues of the final kernel, because we're going to square this thing. Okay. So the question is now, how can we find the eigenvalues of this kind of squared kernel, given what we know? Okay. So here we know that we can write it out in terms of Gegenbauer polynomials. So these Gegenbauer polynomials are orthogonal with respect to the following measure. This here n is the dimension of the sphere. And because they're kind of orthogonal, and I can recover this eigenvalue lambda by solving the following integral. So again, unfortunately, in my handwritten notes I call it zeta. So let's maybe just remember that zeta is equal to k. So I know that my kernel should look like this, okay? So this here, I can also write in terms of Gegenbauer polynomials. So how am I going to compute these eigenvalues? So I've kind of showed you already what happens for Gegenbauer polynomials. In general, note that I could also think about it this way, okay? So if I'm given this kind of thing, I could try and evaluate something like this. Actually, maybe interesting. So note that I can always find the eigenvalues if I find a function in this some kind of space, for which I know the value. Okay? So if I know this function at some kind of special point, then I can just compute the formula. But maybe this is just as a note aside, if you want to kind of go beyond. So how can we compute this? So if we do this, I've decided not to actually do this calculation in this talk, just because I guess it's kind of clear it's going to happen. So we get this, there's some kind of constant. Actually, it's not quite a constant, of course, depends on the dimension of the sphere. But let's not worry about it here, because it's not essential to the understanding. So of course, you can write it out in terms of some matrix. It looks like this. So this here, eta, I will call eta the vector that appeared in the function I'm going to square. So remember this here, I've written it out in some terms of coefficients eta. So I can line them all up. And this here is a matrix of linearization coefficients. Okay, so what are linearization coefficients? Again, here I called it small g, so these are the Gegenbauer polynomials. They tell you if I take the product of two Gegenbauer polynomials, how can I again write it as a sum of Gegenbauer polynomials? So there's some kind of coefficients here, which are called the linearization coefficients. And this matrix will have row and column entries, which are exactly given by this linearization. And I want to start with a very simple example, where I want to, in fact, set S to be equal. Fine. So anyway, so the first case, S equals 1, is obvious. You will all know about it in any book on orthogonal polynomials. In this case, this can just be found by recurrence relations, and this is the matrix, and there's some kind of standard ansatz for this, which kind of means that we're going to take the etas to be in fact equal to these Gegenbauer polynomials as evaluated at a special point, which is a root of the Gegenbauer polynomial of degree A. So it's kind of standard. You can find it anywhere. It gets a bit more interesting in the general case. Okay. And let me just say what we do there. In the general case, we use the same approximation for the eigenvector. So we make the same ansatz. I'm going to write on the vector that is again Gegenbauer polynomials evaluated at some special point. I will also take this to be a root of some Gegenbauer polynomial in the vicinity of L plus 1. And for x equals 2, one can actually also make such an ansatz along these lines exact. And for the general case, actually, this is, I guess, where things become a little bit more interesting, is one has to show, because this will only be an approximate eigenvector, one has to show that there's these fudge terms, like it's not quite an eigenvector, there will be some error terms at the end, that these error terms actually vanish. And the limit that we're going to consider here is we're going to fix L over n, and we're going to take the limit of n going to infinity. So remember, n was the dimension of the sphere, L was the level of the hierarchy. So maybe for the quantum people here, again in quantum, usually you like to think about fixing n, like the dimension of the local system, and then you will take the limit of L going to infinity. Here I'm going to take a different limit, namely we're going to fix this ratio and let n go to infinity. In fact, I would like to emphasize, if you were interested in taking the other limits, it's actually much easier to show that this error term vanish than for this particular limit, but it can also be done. So what happens for the sphere? Let me show you a plot. I'm almost done. So the asymptotic root, so I'm interested in this particular root. It looks like this. And this will give us some asymptotic behavior. I would like to say again, this is kind of exact for s equals 1 and s equals 2. But in general, we study this limit. And I'm going to just show you some plots. Okay. So these are some plots for increasing values of n. Here is theta, so this is the ratio between n and n. Here is this epsilon, so epsilon is like 1 minus lambda s over lambda 0. And it kind of looks like this. So this kind of striped, this little dotted line is the asymptotic bound, and you can see that as n increases, we get closer and closer. So one can also do this for the cube, and the idea is in fact exactly the same. Of course, because these are not Gegenbauer polynomials, they're Groucho polynomials. This means they have different linearization coefficients, which means that this matrix will look different. It will have different eigenvalues, and therefore giving us different bound. Here are also some numerical bounds, and there's maybe just one thing that I want to point out for the cube. Namely, for the cube, the convergence, like the rate at which we approach this asymptotic bound, is actually much slower than for the sphere. So you can kind of see this happen here. Here for the sphere, already we were quite close. Here it takes much longer. So note that also the n that I've chosen here is much larger. So here n goes from 20 to 1,000. Here I had just picked n going from 20 to 3,000. So maybe to say, like, why does this give us a better approximation? So previously, like for the sphere, in this kind of tensor product setting, you would have had something like n over L, or you have n squared over L squared.
For Wells paper, wasn't that like n squared over? Wasn't that? We got something similar, right?
It's exactly the same, but it's for the complex sphere in my case.
Yeah. So note also that what you're doing is the case. Like one can actually understand what they're doing.
Yeah.
In this kernel picture, if you wanted to do that, because you could define a kernel from this, and what you evaluate is the case s equals 1. So this is the case where, in fact, you just have the Jacobi matrix here, and if you don't do this asymptotic relationship for one general. Almost done. So, okay, anyway, so there's what I wanted to say, like I'm discussing this case of the sphere and the cube. But note that there's some general recipe. Basically, you identify the relevant orthogonal polynomials. You find the linearization coefficients. All of this, of course, not so easy. You write the kernel eigenvalues in terms of these linearization coefficients. You solve this eigenvalue problem. And then you solve. course, you don't necessarily have to do this. You can also just guess a kernel and then use that one. If you can compute its eigenvalues, you're in business. But if you wanted to kind of optimize over kernels, then you could follow this procedure. So what have we done? So we have this kind of general method to prove convergence bounds, which works for the sphere and the cube and all kinds of other spaces. And I'd like to emphasize that what we've been doing before, what Andrew and I did before, is a special case of what we're doing here. We can kind of recover this approximate representing measure, and in fact we also get something better for the hypersphere than we did before. So I've not talked about this here. There's, as you might guess, because also Parrilo is involved in this class, so there's a sum of squares picture also. But I'm not going to talk about this here, of course. Fine. And there's some connections to approximation theory in the class. And yes, it is. We're going to talk about it at this workshop soon. So there's maybe a bit too many open questions, and I guess let me just highlight the ones which I think are most interesting. So the first one is, like I said already, in this kind of general theorem, we have overshot our goal, okay? Because we have constructed an approximation that was kind of close to the SDP solution, evaluated any polynomial of that degree. But of course, we don't want to evaluate it for any polynomial of that degree, because we only want to optimize one specific one. And in fact, I guess generally we will know which polynomial we want to optimize in advance, right? I mean, this is sort of the SDP for that. So, for quadratic polynomials, there's indeed something more sophisticated that one can do. But of course, quadratic polynomials on the sphere are kind of boring, so the question is what can we do in general? And there's also another kind of maybe interesting question, which is maybe more to the kind of quantum crowd. So like I said, so we can reprove this kind of real value Definetti theorem. We could also reprove this kind of existing Definetti theorem, this 1.5 Definetti theorem on complex projective space. But it might be very interesting to consider some Definetti theorems for other spaces or other physical objects, for example, in some fermion systems. And the question there is, can we use similar techniques? And there, typically, we will not be optimizing over the kernels, but the kernel will be dictated by the set of states that we want to approximate with. And then, of course, the challenge is, can we compute the eigenvalues of this kernel? And if you can, then, well, that's great. Otherwise, good. Thank you.